Good morning, students. In today's lecture, we will see this chapter, that is Poissons and Laplace equations, right? Okay, already we have covered the vector. In unit 1, we have covered the vector analysis, the Coulomb's law and electric field intensity. In unit 2, we have covered the electric flux density, Gauss law and divergence, the energy and potential. Then in unit 3, we have already covered the conductors, the electrics and capacitance. And today, we will finish this chapter, that is Poissons and Laplace equations, right? Okay, we will start with the today's lecture. Okay, Poissons and Laplace equations. What actually these are the mathematical tools, and why they are used we'll see. Already we have seen the conductors, dielectrics and capacitance. Let me draw the capacitor here. Right, parallel plate capacitor. It consists of two metallic plates. In between them is the dielectric material. This is the dielectric material, what I'm shading it, right? Okay, and we have seen the boundary conditions, conductor to free space and boundary between two perfect dielectrics. All those things we have seen, right? Okay, we will make use of those boundary conditions to determine the capacitance here, right? Okay, here what we are going to study in this chapter: derivation of Poissons and Laplace equations and numericals based on that, right? Okay, we will just, if time permits, I will take up these two topics later, but usually it will not be there. Uniqueness theorem, examples of solutions of Laplace and Poisson's equations. Just I will give the hint what it will be there in this. So I will want to cover this chapter today itself, right? Okay, the topics that are going to cover is we will try to derive the expression for Poisson's and Laplace equation and numericals based on that, right? Okay, we know how to find out the capacitance. C is equal to by the basic definition, Q by V naught. V naught is the potential difference between the two conductors, and Q is the magnitude of the charge on either of the conductors, right? Okay, so in this chapter, what we are going to see, right? So on the metallic conductors, what is first? The potential will be known on either of the conductors, right? So using that potential, just how to derive the capacitance I'm telling, we will try to find out the charge distribution, then the potential difference between the two plates, then we are going to calculate the capacitance. So here we are going to make use of Poisson's and Laplace equations in order to get the capacitance. That we will see how, right? Okay, we will be knowing the potential, and we know the relationship. If I know the potential, then I know the relationship E is equal to minus del V, right? This I know. Then I know the relationship between D and D. D is equal to epsilon E. Is it fine? Okay, I will find out the electric flux density, and making use of boundary conditions. The normal component dN is equal to rho S, right? So using the boundary conditions between conductor to free space, dN is equal to rho S. Is it fine? Okay, once rho S is known, I can calculate. I will come to know what is the charge distribution. How to calculate Q? Q is equal to closed surface integral of rho S into ds, right? Once the charge distribution is known, the potential, we know the potential across each of the plates, and then we can calculate the potential difference. So we have calculated the charge distribution and we have calculated the potential difference, thus we can calculate the capacitance, right? So before proceeding with all these steps, this will come in examples of solutions of Laplace and Poisson's equation, whatever I have listed here, right? But we will not be seeing that, just I have given the hint here. So we will see what is Poisson's and Laplace equations. We will try to derive it, right? Okay. First, derive the Poisson's equation starting from point form of Gauss law. The question another, it can be reframed: derive the Laplace equation. Instead of Poisson's equation, we can ask Laplace equation also. Derive the Laplace equation starting from point form of Gauss law. Okay, both we'll see. Okay, we know the point form of Gauss law already. Del dot of D vector is equal to rho V. This is the point form of Gauss law. Usual form of Gauss law, just I will recall. It is not required here, but closed surface integral of D dot ds, right, is equal to Q, right? This is the usual form of Gauss law. Closed surface integral of D dot ds equal to Q. But we will be using the point form of Gauss law. From this, we will try to derive the Poisson's equation. What is that Poisson's equation? We will see it later. Okay, del dot of D vector is equal to rho V. This is the volume charge density, this, right? Then what is D? D is equal to epsilon E, right? Then what is E? We know the relationship between E and V, that is potential gradient. E is equal to minus del V, right? So del dot of D, D is equal to epsilon E. For D you substitute epsilon E. Then what is the E is equal to minus is taken out, minus del V, right? That is equal to rho V. So del dot of del V is equal to this minus epsilon is taken and divided here. So del dot of del V is equal to minus rho V by epsilon. This we call it as Poisson's equation. So instead of writing it as always del dot of del V, we can write it as del square V. Right? Del square V is equal to minus rho V by epsilon. Right? You can observe once again del V, right, with the variation of potential in different directions. Here it is second order differential equations will be coming, partial derivative del square V, right? So del square V is equal to minus rho V by epsilon, right? So you can observe this equation del square V depends on the volume charge density and the dielectric medium present between the two metallic conductors to form the capacitance, right? So this is the mathematical equation, right? Then next we'll see the Laplace equation. Oh, before seeing Laplace equation, just we will try to write this del square V in different coordinate system, rectangular coordinate system, cylindrical coordinate system and spherical coordinate system. We will try to write this formula. How to write we'll see. Right, del dot of del V. Yes, del dot of del V. Del is a vector operator. Just I will write del here. Del is a vector operator. Dou by dou x into ax, dou by dou y into ay, plus dou by dou z into az. This we know, right? Then we know what is del v also, right? Del v, gradient of a scalar point function is a vector. Dou v by dou x into ax plus dou v by dou y into ay plus dou v by dou z into az. Observe here del dot of del v. So del is a vector and del v is also a vector, right? So the dot product of two vectors is a scalar quantity. What we are getting is a scalar quantity. So take the dot product between del and del dot v. So del dot of del v is equal to, so just multiply the components, dou by dou x of, right, dou by dou v by dou x. So dou by dou x of dou v by dou x, dou by dou y of dou v by dou y, dou by dou z of dou v by dou z. So this can be written as just multiply dou square v by dou x square, dou square v by dou y square, dou square v by dou z square. This is del dot of del v. But I told del dot of del v can be written as del square v. Is it fine? Okay. So in Cartesian system, this is in rectangular coordinate system, del square v is this and it is equal to right. Then in cylindrical coordinate system, del square v, this is the formula. How to write, just I will give you the hint later. Then in spherical coordinate system, this is the formula for of Poisson's equation, del square v, right? So if you remember this Laplace equation, we'll see later. Just I will tell you how to write this, all these three formulas. This in rectangular coordinate system you can write it very easily, but in cylindrical and spherical just you make use of this, right? Del square v is equal to 1 by h1 h2 h3. These are the scale factors in different coordinate system. Summation of dou by dou u h2 h3 by h1 into dou v by dou u. So just I will expand this and write it. Del square v is equal to 1 by h1 h2 h3, open bracket, first term dou by dou u of, okay, h2 h3 by h1 into dou v by dou u. This is the first term. Then next second term is u v w. These are the coordinates, right? U v w are the coordinates, general coordinates. It may be x y z, rho phi z, r theta phi, right? So dou by dou v of, then h2 3 is over, next 3 1, h3 into h1, 2 3 3 1 1 2, like that, right? h1 next will come h2 into dou v by dou v plus dou by dou w u v w, right? 2 3 is 3 1, next 1 2, h1 h2 by h3 into dou v by dou w. So just here what are the scale factors in different coordinate system? Already we know h1 h2 h3. In rectangular coordinate system the scale factors are 1 1 1. This is in rectangular coordinate system. Then in cylindrical coordinate system the scale factors are 1 rho 1, right? This is cylindrical coordinate system. In spherical coordinate system 1 r sin theta. These are the scale factors, right? You know this. So just substitute the value of h1 h2 h3 and corresponding values, right? All this and you will get. So go on substituting here, you will get this formula in rectangular coordinate system, cylindrical coordinate system and spherical coordinates. For divergence we have written, I have shown there. In the same way you write it, you will get these formulas. If you are good at remembering, you can remember these formulas directly, or else you can make use of this general equation in order to write the formula, right? Okay. I hope you came to know how to write this del square V formula in different coordinate system. Next, the same question will continue. Derive Laplace equation starting from point form of Gauss law, right? From this point form of Gauss law, we have derived the Poisson's equation. Next, we want Laplace equation. We'll see here. For Laplace equation, we will assume that rho v is 0 here, right? So this is the Poisson's. I'll write once again. Del square V is equal to minus rho V by epsilon. This is the Poisson's equation. We have derived it, right? Poisson's equation. And we'll assume that the volume charge density rho V is 0. For example, in the dielectric material, if I consider the dielectric material, the volume charge density rho V is 0, right? In between the two capacitors, there is dielectric material. So what about the volume charge? It is 0. Their bound charges exist. No free charges are there. So at that time, you can write del square V is equal to, since volume charge is 0, so I'll write del square V is equal to 0. Is this we call it as Laplace equation, right? But if volume charge is 0 means it doesn't mean that at singular points or singular locations, also we call it as, there instead of volume charge there may be a point charge, there may be a line charge, there may be a surface charge, right, which is responsible for the field. Other than volume charge, there can be a point charge or line charge or surface charge at singular locations, right? At singular locations means where sometimes the mathematical equation will not obey, right? Right? Singular points, I hope you have heard the singular points. At singular locations, there may be point charge, line charge or surface exceptions, we call it as, right? So, if I take the dielectric material, rho v is 0 everywhere, right? So del square v equal to 0 is the Laplace equation. So Poisson's, this is the Poisson's equation and this is the Laplace equation, right? So what is del square v? How to write? Already we know del square v how to write. These are the formulas in rectangular coordinate system, cylindrical, spherical, but equate it to 0, that's all. Instead of, right? So this is the difference. And this Laplace and Poisson's equations are the mathematical equations or mathematical tools in order to solve the boundary value problems. Boundary value problems means conductor to free space, boundary between two dielectric materials, right? Okay, we will take up this numerical, right? If any doubts are there, please unmute yourself and speak to me. Okay, next, calculate the numerical values of V and rho V. The volume charge density is rho V at point P in free space. If V is equal to so and so at point P. This is in rectangular coordinate system. This is in cylindrical coordinate system. This is in spherical. I will be solving part A, B and C. I will leave it to you. Just I will give the hint and leave it to you. Right? So part A I will take up. So find out the numerical values V at point P. So V is given. So at point P, P is what is P? Yes. Part A 1, 2, 3. This is the value of x, y, z. So substitute the value of x, y, z and calculate the potential at point P. We'll call it as Vp, right? So 4 into y is how much? 2. Z is 3 divided by x square plus 1. X square is 1 square plus 1, right? So calculate this. So 4 2 is 8. 8 3 to 24. 24 by 2, right? 2 1 ja 2 2 ja 12 volts, right? So first is over. Next we will calculate the volume charge density rho v at point P. So how to calculate this volume charge density rho v, right? We will make use of Poisson's equation. Del square v is equal to minus rho v by epsilon. So we will calculate del square v and we will multiply minus epsilon and we will get rho v here, right? Okay. Calculate rho v. So we know that del square v is equal to minus rho v by epsilon. This is the Poisson's equation. So we'll make use of Poisson's equation. Okay, another way to calculate rho v, already we have seen in previous chapter, right? So rho v, del dot of d, but we don't know, d is not given. So let me test del dot of, what is d? D equal to epsilon e, and del dot of epsilon, what is e? E is equal to minus del v. So all, instead of doing all these things, it is better to use Poisson's equation, right? So we have seen this already in the previous chapter, how to calculate the volume charge density if electric flux density is given, if electric field intensity is given, right? So first we will calculate del square v. and then we will multiply minus epsilon so that I will get rho v. Is it fine? So in rectangular coordinate system, what is del square v? It is very easy to write this formula, and no need to remember this formula. That is del square v. Just I'll write that general formula 1 by h1 h2 h3 into summation of dou by dou u of open bracket h2 h3 by h1 into dou by dou u. Right? No need to use this formula. Directly in Cartesian I can write it dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. Right? So this is, we will calculate this first. We are calculating LHS. Then we will multiply minus epsilon. Right? Okay, we will calculate one by one. First term, call this as equation 1. So calculate first term, this is the first term, second term and third term. This is the first term, right? We will calculate one by one. So dou square v by dou x square. So, okay, dou square, what is v? V is 4yz divided by x square plus 1. So first we will differentiate with respect to x once, right? Then we will try to differentiate with respect to x another time. 2 times we have to differentiate with respect to x, right? So first we will try to differentiate with respect to x. So 4yz is constant, right? So 4yz can be taken out. Is it fine? So remaining, let me write it dou square by dou x square into 1 by x square plus 1.
Sir, V is 5 rho square cos 2 5 rho.
No, this one, part A I am solving. Part A, V is 4yz divided by x square plus 1. That is part B, 5 rho square, part B. Yes? Yes, madam?
Okay, sir.
Part
Okay,
B,
sir.
I am solving part A. Right? It is 4yz by x square plus 1. Okay, I will continue. Fine. Okay, 4yz is constant. So, we will differentiate with respect to x once. So, 4yz dou by dou x. One time you will. So, this is numerator and this is denominator. So, I remember like this. Den derenum. Just I will write den derenum means derivative of numerator. Denominator I will write as it is. Write numerator and denominator into derivation of den derenum minus num dereden. I hope you remember this, divided by den square. I will make use of this formula. Okay, den means denominator, der means derivative of numerator, minus numerator I will write as it is, derivative of denominator divided by denominator square. So this is numerator and denominator. I will go with this, right? So denominator x square plus 1. Then derivative of numerator, it is 0, right? Minus numerator is 1. I will write it as it is. Derivative of denominator. Derivative of denominator, what I will be getting? 2x. Is it fine? Derivative of denominator is 2x I am getting. Divided by den square. Den square means denominator square. X square plus 1 whole square. I written the formula here. Just I will repeat. Den derenum minus num dereden divided by den square. Alright. If you remember this way, you remember like this. I remember this way. Okay. So once we have differentiated, still we have to differentiate another time. So let me simplify it first. So dou by dou x of, so this will be 0 first term. So what I will be getting? Minus 2x divided by x square plus 1 whole square. So we will differentiate once again with respect to x. So 4yz. Yes, now we will differentiate. The same formula I will apply. Den derenum minus num dereden divided by den square, right? So den, denominator I will write as it is. Denominator x square plus 1 whole square. Denominator. Derivative of numerator. So derivative of numerator I will get minus 2. Minus numerator. Numerator is minus 2x into derivative of denominator. So derivative of x to the power of n, nx to the power of n minus 1. But this is not x, so I'll be getting 2x. I hope this is correct. If any mistakes are there, please let me know, right? Okay, derivative of denominator nx to the power of n minus 1, this is fine, but this is not x, so this I'll be getting 2x. Is it correct? 2x? Yes. If any mistakes are there, please let me know. Divided by den square, denominator square, x square plus 1, already square is there, whole square means 4 to the power of 4 I'll be getting. Yes, this is the first term, dou square v by dou x square. So first term we got it. Similarly, we have to do second term and third term, right? So first term is over. So first term, let me keep it as it is, first term. Finally, at point P only we have to do, we can substitute the value of x, y, z and we can get that, right? Del square v, right? Rho v at point P they have asked, no, let me at point P, let me find out dou square, let me substitute the value of P is 1 comma 2 comma 3. So this is x, y, z. We will substitute the value of x, y, z and we will calculate and keep the first term this as it is, right? We will take up later first term. So I'll substitute and calculate. Okay, before substituting, let me try to simplify. Minus 2, I'll take it here, into x square plus 1 whole square, minus into minus, this will be plus, 2 2 ja 4, 4 2 ja 8, 8x square. Whether this is right or wrong, please let me know it. Please don't wait till the end. I think this is correct. Okay, minus into minus plus, 2 2 ja 4, 4 2 ja 8, 8x into x, x square into x square plus 1, right? So x square plus 1 whole to the power of 4. So let me substitute the value of xyz here in this and I'll calculate, right? I hope this is correct, whatever I have written. 8x square, yes, fine. I'll proceed. So 4 into yz, right? First 4 into y is how much? 2 into z is how much? 3. So I'm getting 24 into, so x square plus 1 I will calculate. X square is 1, 1 square, 1 plus 1, 2, 2 square is 4, 4 2 ja 8, minus 8. Then next, this one 1, 1 square is 1, 1 plus 1 is 2, 2, 2 8 ja 16, 16 into 1, 16 only, plus 16, divided by 1, x is 1, right? 1 plus 1, 2, 2 to the power of 4, 2 to the power of 4 is how much? It is 16. So we calculate this. So 16 minus 8 is 8 only, 8 into 24, 8 into 24, 192 divided by 16. So I'm getting 12 first term, right? After substituting the value of at point P, at P of 1 comma 2 comma 3. Similarly, I will calculate the second term, right? I'll calculate the second term. So second term is dou square v by dou y square. So dou square v by dou y square. So dou square, what is v? 4yz by 4yz by x square plus 1. I hope it is correct. Yes, x square plus 1. Yes. With respect to y, with respect to y means others are constant, right? So 4z by x square plus 1 can be taken out, right? With respect to y, right? So 4z by x square plus 1 is taken out. What I am left out, I'll write dou square by dou y square. So I am left out with only y, right? I am left out with only y. It is taken out. So first differentiate once with respect to y. So 4z by x square plus 1. So dou by dou y of once with respect to 1 means I will be getting 1, right? So this is constant. So with difference, so I will be getting 0. Second term is 0, right? Then we will go to the third term, that is dou square v by dou z square. Dou square v by dou z square. It is always better to do term by term, right? Don't do at a time. So dou square by dou z square into 4yz by x square plus 1. So with respect to z means, so I can take this out, 4y by x square plus 1 into dou square by dou z square of z. So if I differentiate twice, this will be 0. So second and third terms are 0, right? So just I'll substitute in the first term, del square v. How much? First term is 12 I got, right? 12. And it is Poisson's equation. So RHS is what? Minus rho v by epsilon. Is it fine? Okay, I want the volume charge density rho v. It is equal to how much? 12 into minus epsilon. What is epsilon? Since observe here, in free space, they have given free space. In free space means epsilon is equal to epsilon naught only, because epsilon r is 1, relative permittivity for free space, right? For free space, epsilon r is 1, so epsilon equal to epsilon naught. So rho v is equal to minus 12 into epsilon naught is 8.854 into 10 power minus 12, right? So 12 into 8.854. So I am getting it as 106 minus this minus sign as it is, 106.248 into 10 power minus 12 coulomb per meter cube, right? Charge per unit volume, coulomb per meter cube. Just check. Yes, minus 106 pico coulomb. Pico means 10 power minus 12 pico coulomb per meter cube, right? Similarly, you do part B and part C. I am leaving it to you people. Part C is here. Part C. Part B, this is in a cylindrical system. The formula in cylindrical system, you have to use this formula. This is in formula. Do first term, you do it. Second term, third term, and right. Similarly, in spherical, do the first term, second term, third term for part C, right? So for part B, this is the answer. So for part B, this is for part B, right? Rho v will get 0. For part C, this is the answer. Rho v will get 0 for part C, right? Only will get potentials, right? So this is part B answer, and this is part C answer, and this is part A. We have done it, right? Okay. Next, determine whether or not the following potential fields satisfy the Laplace equation or not. Yes, potential field is given. We have to tell whether they will satisfy Laplace equation or not. What is Laplace equation? Del square v equal to 0, right? So volume charge density rho v should be 0. If I do del square v, if it is equal to 0, then I'll say that yes, the given potential equation satisfies Laplace equation. If it is not equal to 0, then I'll write it is not satisfying Laplace equation, right? So they have given three questions are there here. V, this is in Cartesian. This is actually rho. R means rho cos phi means rho phi z means this is in cylindrical. This is in Cartesian coordinate system. Let me write it rectangular coordinate system. This is in cylindrical coordinate system. This is in spherical coordinate system, right? So no need to do it, because once again the same three formulas here. Just I will give the hint and leave it to you. Cartesian means you have to use this formula for del square v. Cylindrical, this formula. Spherical, this formula. You know how to write the formula, I told you, using this equation, right? Just I will take up part A and I will explain you here. Right, v is here, this is in Cartesian, right on, right? So del square v equal to 0 is Laplace equation. So find out del square v first, whether it is 0 or not, check it. So write down del square v, this is in Cartesian, this is the formula. So what is v? Right, dou square by dou x square of v, dou square v of dou y square. So after doing, we will be getting 2. Here we got 2. So del square v equal to 2, we got it. So since it is not equal to 0, so hence v does not satisfy Laplace equation. This is similarly we have to do for cylindrical. Instead of r, you write it rho cos phi plus z. Change it, right, instead of r. Similarly, this is in spherical system. So in spherical, they have solved. Finally, they got del square v equal to 0. Here they got, if del square v is equal to 0, this will tell that it satisfies Laplace equation, part B, for this part B. So I told you, write down v is equal to rho cos phi plus z. For part C, this is in spherical. So use the spherical del square v, the formula, right? So here also we got del square v equal to 0. Hence it satisfies. So the potential field V satisfies Laplace equation, right? The same thing once again. So I want to wind up this chapter. This chapter is over today itself now, right? Because the same thing. If you want, you can. I will give some time. You can solve it later. Okay. I'll stop recording.